Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Amina Diop with us today. Hello, Amina.
Hi, how are you?
I'm doing awesome on this May 24th, 2024 as we record this. So we got a couple of 24s in there. I'm doing wonderful. And Amina, where are you located at?
So right now I'm in Canada visiting family, but I'm a third year graduate student at the University of Virginia.
Oh, very cool. Very cool. So you're up in Canada. How is summer in Canada? Or are we there yet?
Oh yeah, it's very nice. It's very
Very
nice, like very nice warm weather, lots of flowers. It's been nice,
cool.
yeah.
Very cool. Very nice. And I'm in Phoenix, and we are definitely entering into our summer mode for sure. Uh,
Yeah.
we're probably a little bit warmer than Canada, or even Charlotte for that matter.
Yeah.
So you're third year grad student, so let me be the first to say I look forward one day to calling you Dr. Amina. That
Yeah,
would
thank you.
you are so
Yeah.
cool. And Amina, what do you like to do for research?
Yeah, so for my research, I work on protoplanetary disks. So these are disks of gas, dust, and ices that surround young stars. And I'm very interested in these systems because these are the sites where planets form. So to really understand how planets came to be and how we have this diversity of exoplanets that we see. So specifically within this field, I'm interested in the chemistry and how we can use the molecules to probe different physical conditions and disk properties so that I can add more pieces to the puzzle of planet formation.
Cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era. People, go grab a copy for free. Go get one. Disentangling CO chemistry in a protoplanetary disk using explanatory machine learning techniques. And Amina, take us away.
Yeah. Yeah, so this is my first paper right out of grad school, and I work with Dr. Cleese, who's of course my second co-author here. And I also would like to thank my other co-author, Dana Anderson, Jamila Pegis, and Adele Plunkett for all their feedback and for helping with different aspects of this project.
Good show.
So just yeah. So just as just get us into this topic. So I just start with a big picture talking about this. So as I just said, like I use molecules to try to probe different physical conditions and processes. But one challenge we have in this specifically is that molecules are very sensitive to the physical conditions that we encounter in disks. And disks also are quite complex because they have these gradients in the densities, in the radiation fields, in the dust evolution, and that impacts the chemistry a lot. So if you want to use molecules to effectively probe a lot of quantities that we're interested in, we really need to understand this interplay between the chemistry and the physical conditions.
Cool.
And traditionally, the way that we have gone about doing this has been to generate large grid of chemical models and tweak parameters and see how the molecules respond to those changes. And this has been like very useful to understand the molecules and how they respond to all the conditions that we see. But one challenge that we get with this approach is that it's quite computationally expensive to generate the grids. And also we have to choose what parameters to vary so that we can have manageable grid to generate on our like high performance clusters. And
Right.
so that makes it very computationally expensive. And also we have large data set coming out of these models and very complex with so many inputs. So that makes it very challenging to like analyze and
Indeed.
derive a lot of meaningful results. Yeah. So what we were trying to do in this work was to see if we could use machine learning techniques and complement our chemical model analysis with that to derive some useful information and really study these complex relationships between the physical conditions and the chemistry. So
Cool.
that's what we were trying to do in this work. And to tackle this, we focus on one molecule as a test case, and this has been CO.
Okay.
So yeah, so the reason why we choose to work with CO is because it's a molecule that's abundant in disk and easily detected in the submillimeter, and we use it to probe a lot of quantities, including disk mass, turbulence, etc.
Yeah.
And yeah, and so what we found with CO is that its chemistry is more interesting in disk than we initially expected. So
Good.
when we were modeling CO in disks, we initially thought, oh, we just need to account for UV-driven photodissociation in the
Yeah.
surface. and freeze out in the cold midplane of the disk. And so that's what we initially worked with. And one interesting thing that happened was that when we used CO with these models where we include photo dissociation and freeze out, we find that the derived disk gas masses are very low, most of them typically below 1 Jupiter mass. So what that is suggesting is that you don't have enough gas to even form a Jupiter mass planet.
Right.
And so we were like, disks seem to be gas poor. But when we look at another gas mass tracer called HD, and we compare the data that we have for 3 disks with the CO data, we
Okay.
see that the masses that we derive with HD, which is an isotopal log of H2, we see that those masses are 1 to 2 orders of magnitude higher than what we actually see with CO.
Very
When
cool.
we assume, when we assume the ISM CO to H2 ratio of 10 to the negative 4. So
There.
this was suggesting that disks are not as gas poor as we thought, and that there's something actually happening with the CO.
Mm-hmm.
And this is where we had this large grid approach that's been trying to understand what is chemically happening to the CO. And what we found out was that CO is being turned into more complex species like CO2, methanol, CH4, etc. And this whole conversion process is dependent on the X-rays and the cosmic rays and the UV and your dust and all of that. So
All
very
that.
complex.
Yeah.
Yeah. Yeah, and we have learned about all of this using this large grid approach and comparison and exploring parameter space.
Uh-huh.
So this made CO a natural good choice because we have learned a lot about its chemistry over the recent years, and it makes it a useful point of comparison for
Yes.
this approach where we focus on machine learning.
Okay.
So just coming to the last paragraph of our introduction, just explaining the overarching goal of this work. So we are using machine learning techniques, specifically a regression-based analysis, to figure out how CO chemistry is impacted by the physical conditions. And it's important here to highlight that typically when we think machine learning, we think predictions. We want to create a model that makes really good predictions.
Generative.
And we don't, yeah. So we have our inputs, we have our output, and good, like is it predicting what it's supposed to predict? But here we would just did not want to focus on just grading a good predictive model, but also grading a good explanatory or interpretable model.
Good.
Which means a model that allows us to understand how the inputs affect the outputs.
Yes.
And in our case, our inputs are the physical conditions. So here would be gas density, gas temperature, cosmic ray X-ray ionization rates, and UV flux. And our output would be the CO abundance.
Okay.
So we were interested on finding a model that strikes a balance between being a good predictive model and being interpretable.
Yes.
Yeah. And whoever says machine learning, you need some data. So for this work, the data that we use, instead of using this large grid of full disk chemical models, we just focus on a single disk model.
Okay.
Because in one disk model, you already have gradients in the temperature, in your density, in your gradients. So you already have this diversity of chemical environments that in turn impacts CO chemistry. So we just focus on a single disk model for this work.
Cool.
Yeah.
I'm with you. Okay.
Yeah, so now we're gonna talk a little bit about the method, what disk model we use, and how we use the data from our model for the machine learning part. So for this, we use, as I said, a single disk model, and it's a generic disk model, not modeled after any particular disk, just to test this understanding of CO chemistry versus physical conditions. So it's a regular disk around a solar mass T Tauri star with a mass of 0.01 solar masses.
Got
And
it.
also respecting the gas to dust ratio of 100 that we see in the ISM. And we also include some small dust and some large dust. And we make sure to concentrate our large dust toward the midplane to simulate some dust settling that we typically observe in protoplanetary disks.
Oh, yeah. Okay.
So, yeah.
Okay. Very good. Okay, I'm with you.
Yeah, so once we set up this structure, we run our first code in our modeling workflow. So you can go to the next paragraph.
Yep. All right. Okay. Here we go. There's our dust populations.
Yeah.
Mm-hmm.
Yeah. So we perform this radiative transfer with this code. This is code called torus, which calculates the dust temperatures based on the assumed gas and the structure. So once we have that physical structure, we then put it into our UV and X-ray radiation field codes that propagate the photons into the disk. And then we put it into another code that calculates our gas temperatures based on the UV flux and gas density. And then we also propagate the cosmic rays through the disk. And so once we have this model that's sampled for 130 radii and 50 heights, we then put it into the last step, which is the chemical modeling. And specifically for this work, we use the chemical model by Fogel et al. 2011, which has been modified to include some more reactions and some more high temperature reactions, some surface chemistry, and to make it more diverse.
Cool.
And so for this chemical model, we give it 654 species as input and 7,000 reactions that are possible between these species,
Very cool.
including some reactions on the dust grains. We also give it some input abundances to get started. And based on all of that, it calculates the abundance of all molecules in our network, including CO as a function of time.
Very nice.
It does that for 100 time steps between 1 year and 3 million year. And specifically for this work, we focus at a time step of 1 million years since we reached the quasi-steady state by that time. Yeah.
Okay.
Yeah, so that's a little bit about our fiducial model. We also have 2 additional models that we explored on top of that. So we explored one where we have a higher cosmic ray ionization rate that's closer to the ISM value of 10 to the negative 17. And we also simulate a model with a higher initial C to O ratio, because in protoplanetary disks, we typically see C to O ratios greater than unity when we use sub-millimeter lines. Yeah. So we wanted to simulate that and see what effect it would have on CO. So now you can go to figure 1.
Very nice. Okay, figure 1. Here we go.
Yeah.
Okay.
Yeah, so figure 1 is showing the physical structure of the disk and the CO abundance as a function of radius and height. So in each panel, like respectively, we're showing the gas density, gas temperature, the cosmic ray, the X-rays, and the UV. And the last one is the CO abundance relative to hydrogen. Yeah.
Okay. Okay.
Yeah, and what we can see here for all these physical parameters, we see that they span orders of magnitude variation. As I was talking earlier, we have gradients in this gas temperature, gas density, and all of that. The gradient is lesser in the cosmic rays because they can penetrate the disk deeper to higher column densities.
Yeah.
It reduces the variation in the inner disk region. Yeah. Yeah, so we see this variation across the disk, and of course that impacts also the CO abundance that we see throughout the disk as shown in panel F that's showing that result. Yeah.
Yes, yes, yes.
Yeah, and we can also show figure 2. That's on the...
You're just getting that in. Okay, good. I'm with you. Figure 2. Okay, onwards.
Yeah, we can jump to figure 2. Yeah. Yeah.
Bonuses. Okay, let's pull it up.
Yeah, so figure 2 also looks at how CO abundance depends on pairs of parameters just as an initial exploration of our model. And where we can see, we also see that we have this complex function of CO even just between pairs of parameters, and even more complex when we consider these 5 different parameters. So making it a very interesting problem. Yeah, and we could go back up to the next page, to the last page, to the previous page, sorry.
Sure.
Yeah, so I'm going to talk a little bit about our machine learning approach here and how we do this.
Okay.
Yeah. Yeah, so for this machine learning work, for the data, we use that grid of points that make up our full disk models.
Okay.
And each point in that grid, as shown in figure 1, has its own gas temperature, gas density, X-ray ionization rate, cosmic ray ionization rate, and UV flux.
Yes.
And we consider those as our independent variables representing the physical conditions.
Okay.
And in response to that, the CO abundances vary. So that's what we take as our dependent variable. And we extract all of this at 1 million year for that. Yeah. So once we have that simulation models, we then go through and make some changes to the data to prepare it for our algorithm. So yeah, we did some data cleaning, and in the end, we end up with 3,600 individual points as our data sets. And And then we perform like some log transformations since the parameters span various ranges and different orders of magnitude to make sure we are reducing that variation.
Right.
And we also split our data into a training set and a test set, as we typically do in machine learning. Yeah.
Right. Right.
Yeah.
Okay.
Yeah. So
Cool.
yeah, so we follow a 70-30% splitting. So 70% we feed it so that it learns what the trend is, and then 30% of data it has never seen, we use that to test how good our model is by comparing the predictions it makes on that test set with the actual values of the test set. Yeah.
Okay.
Yeah. Yeah, and the other thing we did with this data, we also made sure to scale the data following this robust scaling technique so that we have parameters that are dimensionless and we are comparing apples to apples and removing the effect of units.
Got it. Okay, cool. I'm with you.
Yeah, so we can go to the next page now.
Sure. Figure 3.
Yeah, thank you. Yeah, figure 3 is another figure showing the spread that we have in our physical parameters. So we can again see large spread of conditions that we cover. Yeah.
Yes. Okay.
Yeah. So
Cool.
now into the machine learning algorithms. So yeah. So in this work, we use multiple linear regression and polynomial regression and also some random forest to help in there. And yeah, as I said at the beginning, we are trying to build a good predictive model, but also a model that we can understand and interpret.
Yes.
And with machine learning, as you go through complexity, you get more into this black box regime that makes it much harder to understand the relationship between input output. Yeah. So I want to see if we work with simpler methods like multiple linear regression, polynomial regression, if we could get something useful out of it before we go in the more complex route. Yeah.
Good.
Yeah.
Cool.
So as a reminder, with the polynomial regression, you have your independent variable y, and then you have your independent variables, the x's, so the x1, x2, xn as your independent variable.
Yes.
And they are linked in this equation form where you have your beta values as your coefficients. Yeah, and equation 8 is showing what you have when you go to a polynomial regression where you start adding these higher order terms and cross terms. Yeah.
Okay.
Yeah. So basically, in terms of interpretability, what we were interested in was the value and the sign of these beta coefficients, because they tell us how important different parameters are and whether they're like positively correlated or negatively correlated with CO, which tells us about destruction or formation of CO in the gas phase. That's what we're interested in. Yeah. And we use also various metrics and stuff to check if our models are doing well. Yeah.
Okay. Boom. And sort of an angle. Okay. Very good.
Yeah. So that describes how good our models are doing. Yeah. So now we are ready to jump onto some results that we have found in this work.
Let's do it. Cool. Okay.
Yeah. So we can go to the flowchart is summarizing basically everything we did in this ML approach. Yeah.
Okay.
All our different steps. Yeah. We can now go to figure 5.
Figure 5. Let's zoom that out just a little bit. There we go.
Yeah.
Okay.
Yeah. So yeah, what we are showing in figure 5 is we are comparing the results of using a multiple linear regression to fit our 3,600 data points. So what we are comparing here is just the test set. So that's when we take that 30% to see how well our trained model is doing.
Okay.
So what we are looking at here, we are looking at the predicted CO abundance and the actual. So the actual here means the CO abundance of the chemical model calculated for the test set. And the predicted is what we get from the trained linear regression model.
Okay.
And the purple line that we see in these plots denote the line of one-to-one correspondence. So if you have a point falling on that, you have a perfect match between your predicted and actual abundance. Okay. Yeah, and when we went ahead and plotted that to see how well the model is doing, we see that we have generally a pretty okay agreement, but we have that edge effect that's happening that's highlighted in the black rectangle.
Yeah, okay.
And we see this cluster that's happening. And when we also go to the residual plot that's on the right, and the residual here is looking at the difference between the predicted and actual abundances in log space, we see this line that's also linked to that cluster.
Yeah.
And basically what's happening here is that in the chemical model, you have naturally a maximum CO abundance that you can have, and many points have abundances close to that. So it naturally creates
Got
this
it.
edge at
Got it.
the end that makes it hard to really fit a good model to this. So
Okay.
to deal with this issue, we shifted from working in abundance space to density space,
Okay.
which is more continuous, as we can see in the
Oh
two
yeah.
panels below, where we
Oh,
shift from abundance to density. Yeah. So
gotcha.
we see that with this shift, yeah, we remove that cluster effect and we have a much better agreement.
Yeah.
But when we start looking at the residuals, we start seeing this major curvilinear trends. And what that is telling you is that your algorithm is not picking up all the complexity that's happening. So the linear model is a little bit too simplistic to capture everything going on. So you need to try a more complex algorithm.
Okay.
And so
Good.
that's what we went ahead and did. Yeah.
Okay.
So we can go to figure 6.
Which is gonna be the polynomial. Okay.
Yeah. Yeah. So that's what we then tried with figure 6, where we fit a second order polynomial instead of a linear model and see how well that will do. So again, comparing the predicted abundance from the full polynomial to the actual from the chemical model, we see a
Mm,
pretty good agreement between the two.
nice.
Yeah, and we see also in the residuals, we have less of that curvilinear trend and more of a flattening going on, suggesting that the full polynomial is doing pretty well at capturing what's going on.
Uh-huh.
Yeah.
And what are these like one sigma, the purple horizontal lines? Those are like one sigma or something?
Yeah, so it's showing like a difference in abundances of 1 dex, yeah, between the
Gotcha.
predicted and actual. Yeah, that's
Okay.
residual.
Okay.
Yeah.
Good.
Yeah, so we have a good models. Should be then good to go and just analyze the coefficients. Well, the story was a little bit more complex than
Yeah.
that and having good
Okay.
models. Yeah, it's like anything in astronomy. Yeah, so the challenge that we had, so if we go back to equation 8 at the top,
Yeah.
so
Sure. That was our polynomial.
yeah, so if we go to equation 8, as I said earlier, we're interested in these coefficients. Well, what happened when we transformed from the linear to the polynomial data is that we started increasing the correlation between independent variables. So that means that we have some correlation happening between the different independent variables, like gas temperature, gas density.
Okay.
And that makes it really hard to isolate the impact of each term on the CO abundance. So we effectively introduce something called multicollinearity, and that makes it really hard to carry out this work of being like, okay, this coefficient has this effect on CO and this one without like affecting the other coefficients. So
That would be nice.
we really, yeah, so we really needed to find a way to deal with this multicollinearity so that we can trust the coefficients and isolate their individual contribution on CO.
Cool.
And we talked a little bit about that in the appendix. So we can
Okay.
go to,
Let's slide down to the appendix here real quick. We got 2 appendices in this paper, people. It's pretty cool. Okay, appendix A, random forest.
yeah, we can go to page 12 first, so the next page.
12. Okay, appendix
Yeah,
A, tracking multi. Oh yes, here's where we were. Yes, yes.
yeah. So we need to deal with this multicollinearity because it means that the independent variables depend on one another and affect each other. So we cannot really trust the coefficients directly. So to first check for multicollinearity, we used this metric called the variation inflation factor, or VIF. And what the VIF is measuring is basically it's taking your independent variables and taking one of them and seeing how correlated it is to other independent variables.
Okay.
And it does that for each variable, and it gives a number score to each one of them. And yeah, so and there are different ways you can assess multicollinearity depending on the value of this VIF. So if you have something between 1 and 5, indicates low correlation. If you have between 5 and 10, it's moderate. And greater than 10 indicates that you have a lot of multicollinearity going on. Yeah.
Yes, I'm with you on that one. Sure.
Yeah. Yeah, so when we look at table 3, for instance, when we just look at the linear terms like gas density, gas temperature directly, we see that our variation inflation factor are below 5. So
Yes.
we're good on the linear side. And then you go to table 4 and you start adding all these other square terms and cross terms, you start having very high variation inflation factor.
Wow.
So yeah. So we had to like deal with this if we were to use the coefficients to interpret our results meaningfully. And so the way we dealt with this was to use another machine learning algorithm called random forest.
Uh-huh.
So we can go to page 11
Yeah.
or yes, 11, yeah. Yeah, so we use this machine learning algorithm that's called random forest. And the random forest is a combination of decision trees, which are themselves like algorithms, but they aggregate all these decision trees to reduce overfitting.
Uh-huh.
And so the basic way decision tree works, so we see in figure 12 an example just using a subset of the data, is that you have your data set and the algorithm will perform some calculations to split the data into different boxes to make different categories of data points that are different boxes. Yeah.
Okay.
So yeah, and it runs under the hood to find what are the best splits that reduce the error between your prediction and your calculate value, and it performs that until it reaches a threshold that you said, being either the depth of the tree that you want or the number of boxes and all that. Yeah, so yeah, the interesting thing that we used random forest for was that we put in our polynomial information there.
Yes.
And then from there, we use something called the feature importance scores that
Yes.
ranks your terms on terms of like what's the most important.
Mhm.
So
I'm
that's
with
what we did to find, yeah, what are the most important things in our polynomial, and can we cut down on the number of terms and still preserve the predictive power?
Perfect.
So yeah, so we can go to table to figure 13. Yeah, last figure on the paper.
Yeah, let's slide down there. Getting there, people 13. Ooh, good.
Yeah.
Okay.
Yeah, so figure 13 is showing the importance score that we get for random forest when we put in the full polynomial information. And we can see the ranking of different terms. So it's giving a number score of how these terms impact the splitting that the random forest does. So what we then did from here was to pick terms one by one and to keep track of the variation inflation factor as we include terms to see if we start reaching this threshold of 10, which would indicate that we have some multicollinearity going on.
Cool. Okay.
Yeah. So we kept including terms, and we find that with 10 terms, we are at the limit where we don't have multicollinearity. So when we include the term up to, I believe, T gas times the
Right.
UV field, the next one,
Yep.
that's when we stop having multicollinearity. And we can see in the next table that all the variation inflation factor are below 10 when we use those 10 terms.
Cool. Okay.
Yeah.
Nice.
Yeah. So yeah. So now we can go back to figure 6, I believe. Yeah.
Okay. Good.
Yeah.
Figure 6. Let's back up a little bit. Figure 6, that's 11, 7, and 6.
Yeah. So figure 6 is showing the result of what we called here the simplified polynomial. So it's that polynomial with those 10 terms where we removed multicollinearity.
I'm with
Yeah.
you.
Yeah, and we're showing again the comparison between the predicted and the actual. We're doing a good job still, although less like the full polynomial is doing a much better job, but with the simplified polynomial, we have less of this multicollinearity going on, and we can trust the coefficients more as compared to the full polynomial, and we still are doing better than the linear model. So
Definitely.
yeah, so we were focusing on this model for our interpretation. So we can go to figure 7.
Sure. Figure 7. How many terms are needed? Figure 7. Coefficients.
Yeah, so figure 7 is showing what we've been all along interested in, which are the coefficients of the different terms. Yeah. And just looking at it, what we can see is that the gas density term just has this high coefficient, and it's important. And this just makes natural sense because we expect CO density to correlate with the gas density. So we use it as a gas mass tracer for an important reason. Yeah. The other interesting thing that we see is that we have a bunch of terms that correlate negatively with CO density, and some of them that correlate positively. So suggesting that we have these additional things that are impacting CO and going on in the chemistry that we need to account for. And the exciting thing is that each one of these terms can be like linked back to any specific chemical process that's happening. So
Cool.
If
Okay.
you take, for instance, T2, the term two, yeah,
Uh-huh. Mm-hmm.
that one, for instance, you have gas temperature and UV impacting CO. And this is reflecting regions where you have your moderate UV fields that are not photodissociating CO and your high gas temperature that are preventing CO from freezing out. So it's showing these regions where these conditions are perfect to maintain CO in the gas phase.
Yes. Yes.
Whereas if you start going the negative side, you will have N gas multiplied by cosmic ray, that's T6.
Yes.
Yeah. So you have that term that's showing that gas densities and cosmic rays contribute to reducing CO abundance in some way. And this is reflecting some pathway where cosmic rays can ionize helium,
Exactly.
and that can produce that can destroy CO and form something like C2H or CH4. Or you might have mid-plane regions where cosmic rays can break apart molecular hydrogen and produce your hydrogen atoms that hydrogenate your COIs and form things like methanol.
Okay.
So yeah, so we explain what each of these terms can reflect, and we can match it to some different chemical pathways that are occurring in the disk. And
That's
also something else that's interesting that we see with these coefficients is that we see things acting in pair a lot, except for N gas and T gas with these important terms. So we see combination of gas density, gas temperature, gas density, and UV. And
yes.
this is showing that we need also to start considering physical conditions together and maybe changing them together to see how they impact chemistry and not working on factors one by one. And so this was very interesting to see with
Yeah.
this regression analysis. Yeah.
Very
Yeah. And we also see also in these coefficients that the gas temperature and gas density come up a lot, showing that they're very
important.
important. Yeah. To impact this chemistry, which is again very intuitive. And yeah,
Really
but we also have radiation field and cosmic rays also impacting in other ways. So yeah, so we could see with these coefficients that CO chemistry is indeed as complex as we have seen in the recent years with this regression-based
Yeah.
analysis. Yeah.
Okay.
Yeah, the last bit of piece that was also interesting is that when we ignore gas density and compare what we have on the negative side and the positive side in terms of coefficient values, we see that the negative side tends to dominate a little bit, suggesting that CO tends more toward being destroyed than being preserved in the gas phase.
Okay.
And this is consistent with our observation of CO seeming to be depleted in this from what we see in the ISM. So
Yes. Okay.
yeah. Yeah, so we unpacked a lot of very interesting things looking at these coefficients that are also consistent with what we learned from having this large grid of models and tuning parameters one by one. We see that with a simple disk model and fitting these simple models, we retrieve a lot of results that are consistent
Yeah.
with what we have found.
Yeah.
Yeah,
What I like about this one is the decomposition into physical effects,
yeah,
right?
yeah,
Physical properties, right? It's very cool. Mhm.
yeah, yeah. And we can
Okay.
go to the next page where we
7
do,
positive. We talked about negatives and figure 8.
yeah.
Multiple regressions. Okay.
Yeah, so in figure 8, what we did was we were wanting to look at, okay, does any of this fitting change when we just look at this region called the warm molecular layer, which is the region we typically probe when we study CO due to optical depth effects. So this is a region a little bit above the cold midplane. So I wanted to see what will a regression analysis reflect on this region, and does it differ from studying the whole disk
Oh,
chemistry?
okay.
Yeah. Yeah, so we isolated this region that is in temperature between 20 and 100 Kelvin. And we took those points. We also followed the same data cleaning steps and split it into a training and test set.
Yes.
And here we are looking at our test set. And we are again looking at the predicted CO density and actual for this region.
Okay.
And when we fit a multiple linear regression, we see that we have a pretty good fit between the predicted and the actual,
Yeah.
plus some outliers that we'll talk a little bit about, which are highlighted in black.
Yes.
And yeah, and we see something similar when we look at our residuals, where we see that they are very low for most points, and we have these outliers happening.
Yeah.
But we have pretty good fit happening with this
General.
multiple linear regression. So no need even to go the polynomial regression route. Yeah. So now what's interesting is like, why do we have these outliers happening
I
and
don't
not like
know. Tell me, tell me.
Yeah. So we can go for that to figure 9. So we start to see, okay, what are the physical conditions for these outliers? So here we are showing the distribution of the gas temperature, gas density, and all of that for this warm region that we excluded, and comparing that to the distribution of the outliers.
Yes.
So it's important to mention that the outliers are actually 20 data points out of these 500 points that represent the test set. So it's a very small number.
Yes.
But what we see here is that the outliers are mostly located at the edges of parameter space.
Yeah.
And yeah, and specifically looking at it, we see that they are located in high temperature regions and high UV regions. So that could be denoting this transition region where you're starting to go in this region where you have the UV and the temperature happening and starting to modify CO and breaking it down.
Cool.
So
cool. So you're
yeah,
getting a transition, right? You're getting a transition from one to the next.
To the next, yeah. So most of the point in the warm molecular layer follow this linear model, and I fit well by that, but these outliers start going through this transition region. So
yes,
they are reflecting a different chemistry occurring. Yeah. So all in all, we can say that with this warm molecular layer, we are fine with the multiple linear regression, whereas with the full disk, we need this multiple polynomial model. So that means that the chemistry is less complex in this warm molecular layer as compared to what we see with the full extent of the disk. And this is suggesting that temperature reduces the level to which CO is getting transformed in this other species and being depleted, which is something we have also learned and consistent with previous work, where we find temperature reduces this complexity.
Yeah. Yeah. Cool.
Good. Yeah. Yeah, that was exciting. Yeah, the last 2 parts I'll touch very briefly on. We also looked at the effect of changing the cosmic ray ionization rate and the initial C/O ratio. Yeah, and the age, yeah, and we compared that with the fiducial model. So this is looking, we use random forest to perform this analysis and informed by what we learned from the fiducial model. Yeah, and what we see here for the terms is that when you start going to the high cosmic ray and high C/O, all these terms become more important than what we just see with a fiducial model. And when you start looking at like the negative terms versus positive terms, you start to see that these negative terms really start to like dominate in these models. And what that is suggesting is that you are increasing CO depletion as you increase the cosmic ray and as you increase the C/O ratio.
Okay. Yes, makes sense.
Yeah. Yeah. Yeah, and that could be understood when you increase the cosmic ray, you increase things like H3 plus and He plus that can destroy CO and help it turn into other species.
Yes.
And when you increase your C/O, you can help favor the production of hydrocarbons. So having your carbon locked into this C2A, CH4 instead of being locked into CO as you increase the C2O. Yeah. Yeah. And so we can then go to section 4.4.
4.4, putting it all together. There we go.
Yeah. Yeah, so in section 4.4, we summarize everything we've learned about this approach of using simple algorithm like multiple linear regression and polynomial regression. So we find that with this approach, we see things that are consistent with what we learned about CO chemistry using our large grid of models and seeing changes. So we find notably that there's a tendency towards CO being depleted. We also find that with higher cosmic ray rates, we can increase CO depletion. And we also find that with warmer temperatures, CO processing is being reduced. So all in all, this is doing pretty well and showing that machine learning techniques could be a useful complement to our chemical modeling efforts. And this is with working with simple algorithms that can fit within minutes of the data. And so we can even go more complex and try more techniques. And even there are more tools that are being developed to make machine learning models, not just black box models, but more interpretable. So that could be something that
Yeah.
can be explored in the future. Yeah.
And we'll come to that future here in a bit. Very good.
Yeah.
Very cool.
Yeah.
Very
So that's
cool.
a quick overview of this work. Yeah.
Yeah, Amina, that was awesome. Thank you
Thank
so
you.
much for walking us through your very lovely article. And you kind of touched on it a little bit there at the end. So let me go ahead and push on it a little bit.
Mhm.
Excuse me. And ask, where do you think we go from here, given the published article? Is there additional data sets so that one could crank up either the training or the testing by a factor of 10? Maybe there are other wavelengths. You mentioned some other techniques of machine learning. So maybe those would be applicable or give some more information. And so just generally, where do you think we go from here, given the published article?
Yeah, so this was, as I mentioned at the beginning, this was like to test like if machine learning techniques could be helpful in understanding how physical conditions affect molecules. And this was with one molecule, so we can test it with more molecules that we detect in this, N2H plus, HCO plus,
Yeah.
or even other quantities that we're interested in, like cosmic ray and all of that. So we developed here a template that could be followed and expanded with even more complex models that include some depth dynamics, which is something we don't have in our models yet.
Ooh, right.
So we
Yeah.
can do
Yeah.
something more complex. Yeah. But in general, the field of like disk chemistry is just growing and very exciting because we have all these large disk survey that are being carried out with ALMA, but also JWST that are happening.
Right.
So that means we will have a lot of disk data set coming out. And I'm even part of one program led by my PI called the Disk Exoplanet Connection, or
Yeah.
DECO for short, where we will observe 80 disks with ALMA with 25 different molecular lines, and also have a JWST follow-up program. And I'm building like the tools to analyze the data and make sense of it and squeeze out information like C2O ratios and disk masses, and try to connect that with what we know about exoplanets and see what we can learn about processes and formation histories of planets. And we also have many more other large programs that are being carried out for this chemistry. So we're expecting to have a lot of data, but also trying out with different machine learning tools in different ways, like especially speeding up modeling techniques or just finding ways to interpret the data and extract meaningful information.
Awesome. Awesome. So one, I'm really looking forward to seeing this field develop over the next couple of years. It'll be very exciting. And number two, I predict a very exciting thesis. It will be awesome. Amina, thank you so much once again. Really appreciate it.
Yeah, yeah.
And
Thank you for having me.
oh, sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.